All right. Hi, everyone. So sorry about being a little bit late today, a little hectic, so my apologies. I'm going to enable editing so I can actually this slideshow. So let's go through this. All right. So yeah, hi, everyone. Final exam review. So today we're going to go over a review, primarily on tree sorting, sets, maps, and hash tables. On this review in particular, I don't think we go over like some topics like heaps a lot much, but we'll go over all the topics on here. So yeah, really, this is just aimed at providing a high-level review for reference. It's not comprehensive, as we mentioned, but it does hopefully cover the content after exam one. Okay, so yeah, so under review, we're in for sets, maps, and hash tables, and then we're going to cover sorting and then trees. So first, sets, maps, hash tables. Hopefully, all these are familiar to you. If not, then you gotta get studying, I guess. But that's okay. Yeah, the things to know are the rules, the sorting steps, and the algorithmic complexity of the different things. So for example, what's the output of the following code? And so this tests a little bit your understanding of a data structure. So go ahead and pause and try and answer it maybe. All right, and we'll go over it. So what do we notice? Well, first we insert 1 into our set, and then 37, right? And then 45, and then 6, right? So we've so far 4 different things. And then we insert 37 again. Well, when we insert 37 again, notice it's already there. So what happens when you insert something into a set? It's already there? Nothing, right? Like a set cannot have duplicates because it's like a set in math is the same way, right? You can't have duplicates. But for C++, like there's no problem with that. And programming languages in general, there's no problem with adding something to a set. It's already there. I mean, it doesn't do anything, right? Because it's already there. So it doesn't give an error. It doesn't like not compile. It will compile, but yeah, it's just not going to make an effect because you can't have duplicates. So it's just going to basically do this, not insert, right, not insert. Then we erase 1, so it's going to erase the 1. And we're just left with these 3 elements. So hopefully we should get size of the set is 3. Yeah. Okay, let's hope that makes sense. All right, so sets, so as mentioned, sets are a collection and they don't contain duplicate elements and they're not indexed, so there's no ordering to them. And yeah, no inherent ordering. And the entire idea of the set is you can insert and then you can like test for membership. So you can insert, remove, and then find. So like see if something exists in the set, insert into the set, and remove from the set. And that's what a set allows for. And yeah, it allows removal. Okay. So will an error be generated if you insert a key value pair into a hash table that already contains that key? I'm trying to answer that. Okay. So the answer for this is no, there won't be an error, right? And there's no error because if you insert a key value pair that's already in a hash table that already contains that key, it's just going to replace it. It's just going to replace that value, right? Or the key value pair with this key value pair, pretty much, right? Because like you can't have duplicate keys, but it's just if you try and do it again, it's just going to replace it. It's not going to have a problem. So that would be like if for example, if I have a map, let's just say I call it map, right? And I just do something like this. Like it'd be, yeah, an unordered map, right? But let's say I do map. Maybe if map 5 is equal to 6, maybe it's a map of integers to integers, something like that, right? And then on the next line, I do something like this, map 5, 7, or 5 equals 7, right? What's going to happen is at first, the map is going to have this pair in it, right? 5, 6. But then once it gets to the next line, it's just going to replace this because you can't have duplicate keys in a hash table. So it's going to work something like this. It's going to look like this, and it's just going to replace this. Okay. So, but there's no error with that. There's no problem. Okay. Cool. Okay, so moving on. Which of the following are properties of good hash functions? So yeah, just want to mention. Okay. What are good hash functions? So yeah, you can try and answer this one too. Okay. I mean, so yeah, you can pause if you'd like. So a good hash function will absolutely run in constant time. Like that's a property of hash functions that just should always be true, right? It should always run in constant time. And given the same input, results the same output every time. this is also absolutely true, because what happens if this isn't true? Let's just consider what would happen. So let's say that we have, let's say, for example, if we had that as our hash function, let's say in our map, right, like maybe 5 in our map will go to bucket, I don't know, let's say it goes into bucket, like some random bucket, B, right? So we have a pair 5, let's say our pair is like 5, 7 again. So then in our bucket, right, we're gonna have 5, 7. The problem is like, this is in bucket B. But if it's not determinate, if our hash function isn't deterministic, the next time we try and like hash 5, and if it's not deterministic, it'll give us a different bucket. So let's say it gives us bucket B2. Well, in bucket B2, 5 isn't there. So because it's not deterministic, it's not going to find it here because 5 isn't there. So it has to be deterministic, right? If it's not deterministic, you're not going to find the element, and that defeats the whole purpose of a hash function. So that's why, hopefully that explains why that's the case. But the why maybe isn't as important as to know just that's the case. But I think sometimes knowing why helps understand like the whole idea together. But okay, so yeah, the properties of good hash functions are running in constant time and the fact that it's deterministic. The next two are not as important. NP complete, well, we don't want it to be NP complete. That would be actually pretty bad. That would be very, very, very slow. Well, with what we know now anyway, that's slow. So that would be bad. And differentiable, and by we know now, I mean everyone, like not just this class, as far as NP complete is concerned. But okay, differentiable, that's not important either. So yeah, it's really just these two running in constant time, the fact that it's deterministic. Yeah. Okay, cool. So how about this one? The standard library, what is the time complexity of reforming all hash table functions? Okay, so let's go over this. So as we know, right, we know how hash tables work, right? So for insert, for remove, for search, like all of these, ideally, we have the time complexity of O1. And the reason why it's O1 is because, well, we've actually talked about this a fair amount, right? It's like when you, again, just knowing the fact that this is O1 is most important. But on average, like the average case where, or not just the average case, but amortized, which we don't want to talk about amortized analysis so much, but like in general, it's going to be constant time because the hash function is constant time. So you find the bucket in constant time, and then you can just insert into the list in that bucket, which should be constant time because you have many buckets. That's why we work with load factor. So we're expecting like less than 1 per bucket. So hopefully you don't have to go through anything, you just put it in the bucket. And then when you want to find it, again, the load factor is less than 1. So there's on average less than 1 per bucket. So it's constant time to find the bucket, and then it should be constant time to actually find it in that bucket. So that's how we get a 1. Again, main takeaway is the fact that we just have to know that this is a 1. But that provides a little bit of explanation as to why we say it's a 1. Okay. So if that's our hash function, string size mod 10, what index will the string algorithm be stored in the hash table? Okay, so you can try and answer. And now we're gonna go over it. So, okay, first let's find what algorithm mod 10 is. Well, algorithm length mod 10 is, right? Because it's string size. What is the size of algorithm? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 mod 10. Well, oopsies. What is 9 mod 10? That's just 9, right? Because 9 divided by 10, what's the remainder? It's 9, right? It's 0 remainder 9. So we get 9 as our modulus. And so, yeah, this is the index we'll be storing in our hash table, is 9. That's pretty much all there is to it. And there we go. Okay, so what's the load factor of a hash table of capacity 50 with 30 values in it? Okay, let's calculate this. So, yeah, you can try and answer it. You can pause if you want, and we'll go over it. Okay. So to find the load factor, remember, is just the number of values in the hash table divided by the capacity of the hash table. So in this case, that's just 30 divided by 50, which should be 0.6. And that's all there is to it. Okay. Question number 7. If we want to maintain a load factor 0.5, we have an array of current capacity 20. When do we increase the capacity of the array? So go ahead and try and answer. And pause. We'll go over this one as well. Okay. So to solve this problem, you have to remember that we increase the capacity of the array once the load factor is met. So as soon as we have a load factor of 0.5, we increase the capacity there. So just thinking about it logically, right? Like, you'd be like, oh, okay, when do you reach 0.5? That's when half of the things are filled. What's half of 20? It's 10. But to just calculate it out, we have to increase the capacity of the array when we have the load factor times the current capacity. That's when we have to increase the capacity, because this is when we filled enough elements to actually meet our load factor. And that's when we reach 10. So once we reach 10 elements, when the array has 10 elements, is when we will increase the capacity of our array. So it's not 11 because we do it when the load factor is met. Okay. So it's 10. All right. Cool. Okay, so next problem. Next problem. Let's talk about hash tables a little more. So we talked them a bit. But remember, they're a non-ordered data structure that store key value pairs. So a hash function is used to compute the index for data. So you do the hash, just like we saw the algorithm, string size mod 10 gives 9. So the hash function computes the index for the data, and then hopefully it evenly distributes. It's random, and being random is important because it being random means that it's equally likely to be placed in any bucket. And that's good because that means that each bucket on average is only going to have like one thing. If it weren't random, then all of them have all of them, like all the values would be one bucket. That would be bad because then that defeats the whole purpose of having hash. But okay, so that's why, or it should not be random. Okay, sorry. So it should randomly distribute things. It should evenly distribute. That's what I mean, evenly distribute. It should not be random in the fact that each time you put something into your hash function, it should give the same thing out. So it should evenly distribute. So in that regard, it should be random, but it shouldn't be random in the sense that each time you compute a single hash, it should give this, or a hash of a single anything, right? You take the hash of a key, it should give the same result. And easy to compute in the sense that like you should be able to compute it at one time. And remember, the load factor is the number of elements divided by the size of the array. A higher load factor means a higher collision rate. And what that means, and it's a slower hash table, because if you think about it, a higher load factor means that you have on average more elements before you have to rehash, right? So for example, if I have a load factor of 0.9, then that means that I'm more likely, like even though it's less than one element per spot, right, per bucket, on average, like even though that's on average what I'm going to expect, like in practice, I'm going to expect there to be some collisions, right? Some of them will be in the same bucket. And if they are, that means longer chains. So higher load factor would mean longer chains in a bucket, in some buckets, right? Because there's a higher collision rate, which means slower hash tables. That's an explanation as to why, but you can also just think about it, higher load factor, higher collision rate, slower hash table. That's why. Okay. And again, we dynamically change the array size to maintain a load factor. So if the load factor is met, we have to increase the array size. So for example, we have an array of size 10, and we want to maintain a load factor of 0.8. As soon as we insert the 8th element, we meet the load factor, we increase the size of the array. So maybe then we would double, for example, the size of the array. So we have an array of size 20 now, for example. And now the load factor is what? Well, I have 8 elements, size of 20. So now the load factor will cut in half, so it's only 0.4. Okay. Okay, so now poll question number 8. So which collision resolution scheme is more suited for a situation with a high load factor and the hash function x mod 10? So maybe you don't remember these, hopefully you do. Okay. All right, so the answer for this, you can pause if you want, but the answer for this would be chaining. And the reason why is because the problem with open addressing is that with the, okay, well, let's look at the answer. Yeah, separate chaining. And the reason why is because the problem with open addressing is if you have a high load factor, right, you're likely to have some collisions. With open addressing doesn't deal with collisions by placing things in the same bucket. It tries to find an empty bucket. And if you have a high load factor, right, you aren't going to have very many open buckets because you have almost the same number of, like once we get, for example, a load factor of like 0.9, right? We have 9 out of every 10 buckets right before we have to rehash. 9 out of every 10 buckets is going to have something in it. So if we're using open addressing, then that means like we're going to have to, on average, like check about like 9 buckets, right? At the end, near the end, we're going to have to check 9 buckets before we find one that's empty. Whereas with separate chaining, on average, each bucket still only has like less than one thing. So even on the 9th one, we might only have to actually go down like through the list 0.9 elements on average. So it's much, much better because as the load factor gets high, for open addressing, you're gonna have to find like, with open addressing, you're gonna have to like look through more and more things. Whereas with separate chaining, you find your bucket and then you won't usually have to go through many things within that bucket. With a small load factor, that might be different. You might want open addressing because there are a lot of empty buckets. Yeah. And as we see here, this is exactly what we see, right? Is the average cache misses per lookup. So on average chaining, right, you have to check more things at smaller load factors, but at larger load factors, like open addressing gets really, really bad, but chaining remains about the same. So that's why our answer is separate chaining for high load factor. So let's remember the collision resolution schemes. So for open addressing, when there's a conflict, we look at subsequent spots to where to put the data, right? So if our hash table looks like this, and we have data like here and here, maybe an open spot here, for linear probing, what we would do if we want to, like I'm just numbering them, but like let's say we have data in this way. And now let's say our hash, we get 3, like we want to put a 3 in, and it hashes to the 0th index. Well, there's something there. So we need to go to the next index and then go to the next index before we finally find an empty spot. So that's how linear probing works. You probe subsequent spots one after another. But the problem is, it suffers from clustering, right? Because like now, if I get any, like even if this is larger, anything I get from 0 or 1, like or 2, right? I'm gonna have to keep moving over and moving over. Like there are 3 possible spots where it's gonna have to go here, right? So you're gonna start to see clustering because there are more spots that end up, like there are more possibilities for the hash, which force it to be near the other ones. And that's a problem because they're all gonna cluster there. Because even in a large hash table, if I already have an element there, well, guess what? What are the odds, or what's the chance, even in a large hash table, what's the chance that I have to get the one right, that I end up with the one right next to my current one? Well, if I'm using linear probing, I can either land on that spot that's next to it or the original spot. Either way, I'm gonna have to end up in this position. And so it's the most likely one to choose. So you're gonna start to see clustering. That's why we see clustering. That's a problem with open addressing. Quadratic probing is a little better because it helps to resolve a little bit of this clustering, because the distance between probes increases quadratically. So rather than just checking one next to each other, you check like 1 and then like 2 and then like 4 and then 8, 16, or 1, maybe it's like 1, 4, 9, 16, 25, and so on. And so it's a little bit better. But it still does have some problems that open addressing has, right? With the high load factor in general, it's still gonna have a problem in which you might have to check a bunch of locations, but it does fix a little bit of the clustering problem. For chaining, chaining is generally what we see the most, I guess, is like where each bucket, like you can think of the hash table as a bucket or as an array of buckets, and then each bucket has a linked list. So for example, right here, maybe I have data that's like 1. And if I get position 0 again, rather than having to check, oh, okay, let's move over to position 1, it's just gonna put, like now if I have a 2, it's just gonna put the 2 here. So of course, to find the 2, it's a little bit, might be slower if I have to like look through the 0, but it might be better because I don't have to like go, oh, here, no, it's not there. Oh, here, no, it's not there. So, and then keep going this way. You just have to go down one list. So it does not suffer from clustering because it doesn't have that problem like we mentioned earlier of being more likely to choose position 0. Like now position 0, every position is still equally likely. So it's not gonna have the clustering problem. And it doesn't require iterating through this list this way to find the value. And if a conflict arises, you just add the element to the end of the linked list. Each index in the array stores a linked list or a vector, like we see here, linked list. So this chaining can be, in some cases, a lot better, for example, with higher load vectors. Okay, that's closure resolution, just for review. Okay, so question number 9, true or false? Maps in C++ are implemented with a hash table. All right, you can pause if you want, but we'll go over this right now. The answer is actually false. This is a little bit of a trick question, right? Because maps in C++, we're talking about, when we say maps, we don't mean unordered maps. Unordered maps are implemented with a hash table, but regular maps are actually implemented with a binary search tree, or a balanced, sorry, they're implemented a balanced binary tree. That's what I meant to say. Yeah, that's false. Yeah, okay, binary search tree. And unordered maps are implemented with a hash table. So there we go. So just to keep in mind, unordered maps, hash table. Ordered maps are just called maps in C++. They use a binary tree. So yeah, maps are implemented as balanced binary search trees internally. They use red-black trees, and values are inherently sorted because it's a red-black tree and it's balanced, right? Balanced trees, and the fact that it's a binary search tree is what allows them to be sorted. So time complexity of all operations is O log n, because remember, insertion into a balanced binary tree, or balanced binary search tree, right? Insertion is log n, removal is log n, and find is log n. Unordered maps, though, because they use hash tables, time complexity of all operations is O1. So there are benefits to both, though. Like in general, if you're doing something that doesn't matter with order, unordered maps can be better. But if order does matter and you need to have it sorted in some way, then ordered maps are great. Yeah. Sorting. So for sorting, things to know are pseudocode, sorting steps, and algorithmic complexity. So what's the best case time complexity of insertion sort? Okay. So if you don't remember, okay, well first go ahead and try and answer. But if you don't remember, now we'll go over it. What is insertion sort? So insertion sort is, let's say I have something like this. I'm going to go ahead and say in my array looks like this. Let's sort it ascending, right? So going up. So ideally, when we have it sorted, it'll be 1, 4, 5, 6. But okay, remember insertion sort in the first pass, you just compare the first two elements, or like you sort the first two elements in the first pass. So 4 is less than 5, so you're going to end up with 4 or 5. After the first pass, this is what you have, and everything in the first two elements is sorted. Then you add your next element to the sorted portion. So 6 is going to be added to the sorted portion. So you move it left until it's in the right position. Actually, here it's already in the right position, so we don't have to move it left at all. Then we add 1 to our sorted portion. So 1 is going to swap with 6, then 1 is going to swap with 5, and then 1 is going to swap with 4. So at the end, it's just going to look like this. So that's what insertion sort is. But what happens if, like, it's okay. But remember, best case time complexity, that has to be something that has to do with specifically the input that you're given. It has to be some property of the input. So for example, let's say I'm given an input that is itself sorted. So 1, 4, 5, 6. What do we notice? Well, we notice that I sort the first 2 elements. I don't have to move 4 at all. I sort the first 3 elements. I don't have to move 5 at all. Sort the first 6 elements, or first 4 elements. I don't have to move 6 at all. So each time I'm doing just one check. And how many checks do I have? How many times do I have to do that? Well, n minus 1, right? The length of the array minus 1. So n minus 1 times just one check. So in the best case, insertion sort is just on, right? Because being sorted is like a property of the input. So we can use that for best case. So on. Okay, so which of the following are true? Pause and try and answer it. Okay, so bubble sort works by comparing each element to the first element in the array. This is not true, because what bubble sort does is it just checks like this element against the one next to it. And it keeps doing that until the whole thing is, until the whole array is sorted, until it makes no swaps in a pass. It has O(n) squared time complexity? Absolutely, because if you think about it, I mean, we know that, well, remember, we know that it's just O(n) squared. It's one of the O(n) squared ones. But this is true, and you can go back to this discussion if you want to, but we know this is true because each pass, you might have to make n minus 1 passes, and in each pass you have to make like n minus 1 comparisons, right? So that's of order n squared complexity. Order of n space complexity. So when we say space complexity for this class, we mean auxiliary space complexity, or like extra space, how much extra space is used. So with bubble sort, you use the original input array. So you don't have to use any extra space. So just O1, because you're using the original array. So it's not O(n) space, it's O1 space. So the first one is false, second one is false, first one is false, third one is false, second one is true. Okay, so which algorithm sorts by repeatedly moving an element around a pivot? Pause and try and answer this one as well. Okay, and the answer for this is quicksort, right? The whole idea of quicksort is each time, like recursively, you choose a pivot, and then you move, then you like sort everything in, you move everything that's smaller than the pivot to the left of the pivot, move everything that's larger than the pivot to the right of the pivot, and then you recursively call quicksort on the left half and the right half. And at the end, you'll have a sorted array. That's how it works. Okay, now which of the following are considered O(n) squared sorting algorithms? Okay, so you can pause if you want to, but we'll go over it right now, actually. The answer for this one is bubble sort is O(n) squared. As already mentioned, quicksort is not O(n) squared, because quicksort on average, okay, randomized quicksort in the worst case could be O(n) squared, but on average, like we don't say O(n) squared because it actually performs like O(n) log n. As is, and heap sort is actually O(n) log n, because it's just putting things into a heap and then removing them from the heap. But removal from a heap takes log n time. They're n elements, and building the heap only takes O(n) time. So it's O(n) plus n log n, which is n log n. Selection sort, on the other hand, is each time you go through, you choose the largest element. So you have to choose the largest element the first time, and the largest element, like the largest element they haven't chosen so far. So that's, you have to check n minus 1 elements, or you have to check n elements the first time, n minus 1 the second time, n minus 2 the third time. And if you sum all of those, that's O(n) squared. So we consider selection sort to also be an O(n) squared algorithm. So it's bubble sort and selection sort. Okay, so which of the following is not an in-place sorting algorithm? All right, so for this one, of course you can pause as always, but we'll go over this one now too. Well, selection sort, you're just choosing the largest, right? Each time that you haven't, like the largest you haven't chosen so far. That you can do in place. So that's in place. Okay, and then heap sort is also in place since like you're given an array to start with. So you just turn the array into a heap. And remember, heaps can be represented with arrays. So you actually don't need any extra space. And with quicksort, you don't need extra space either. There is a space complexity of log n used, but that's because the like call stack, recursive call stack, causes space to use, but it doesn't require like extra space for the array. The array itself, you're just using one array. Merge sort, on the other hand, each time you go through, like it takes O(n) extra space. And the reason why is because each time like you want to do a merge step, you have to actually like separate the two arrays. And in order to do that, you have to make the space for the extra arrays and then merge them together. So like when you merge them, like you have to allocate space for the merged part. And so in total, you have to have one extra space. So merge sort is not in place because it requires you to have extra arrays allocated. So the answer is merge sort. Okay. So sorting algorithms description. So we've gone over these all a little bit today, but selection sort repeatedly selects the minimum unsorted element and moves it to the end. Insertion sort repeatedly grabs the first unsorted element and iterates through the sorted selection or section to find converted insert. And both those are O(n) squared in the first case. Bubble sort, as mentioned, repeatedly swaps adjacent elements if they're in the wrong order. That's O(n) squared. Merge sort halves the array, recursively sorts each half, and then merges them. So n log n. Quicksort O(n) squared, but we consider it to be n log n because on average, and it practically is going to always be n log n. The odds of it performing O(n) squared on a large input is like negligibly small. Yeah, because as long as it chooses a good pivot, it'll perform like n log n. And it doesn't even have to choose a good pivot, it just has to choose like a not like the worst pivot each time, which is very likely on a large input. So yeah, choose a pivot, sort the elements around the pivot, and then recursively sort some sections, dimensions. So yeah, the heap sort is just add all the elements to the heap, remove them from the heap, and log in. Okay, now we're on to trees. So trees we'll talk about now. So tree traversals, we pre-order, post-order, and in-order, but we'll skip those for now. BFS, which is just level order, and DFS. DFS on a tree is just pre-order, post-order, in-order. And binary search trees, we'll skip heaps for now, or for today. We'll talk about Huffman trees as well. So tree traversals, traversals are used to go through elements of the tree. There's several types of traversals we talked about. There's pre-order, in-order, and post-order. There's also level order. And time complexity for all traversals is O(n). And that's because you have to go through all the elements, right? So if you go through all n elements one time, that's just O(n) time, right? So, okay. So here's the poll question for you guys. Given the following tree, which of the following valid permutations of orders in which the nodes access is breadth first search algorithm? And yeah, access just means when the property is used. So, right. Okay. So you can pause and try and answer it, but we're going to go over this. Breadth first search. So breadth first, if you remember, is really just level order traversal. So for level order traversal, we're going to start at 5. So all of these have 5. Okay. And then we have option we can go left or right, but let's go this way first. So let's say we go 3. We go 3, 6, 1, 4, 8, 2, 7, 9. So that's one option. So 5, 3, 6, 1, 4, 8, 2, 7, 9. Oh wait, sorry, that's wrong. Wait, no, it's sorry. 5, 3, 1, 4. No, sorry. 5, 3, 6, 1, 4, 8, 2, 7, 9. Okay, yes. So, all right. Or alternatively, what we can do is we can prioritize going right instead of going left. Because again, with the level order traversal, right versus left doesn't really matter because we're only at the level we're at. So instead we can go 5 and then 6, 3, 8, 4, 1, 9, 7, 2. So let's see. 5, 6, 3, 8, 4, 1, 9, 7, 2. That's valid. So our answers would be A and C. There we go. Yeah, the whole idea of breadth first, right, is its level order. So we add the non-null children of the node that's access to a queue. We search level by level. You never search the node of a greater depth. You never go like further down the tree than you currently are, right? Like anytime you're accessing a node, you must have visited everything above it already. That's basically what it's saying. That's because that's just how BFS works, right? You're like with BFS, because level recursion is a BFS. With BFS, right, you're not going to access something that's like 1 away from your source before you or after you access something that's 5 away from your source. That's not how BFS works. That's not how level order traversal works. So that's all. That's what this last thing is saying. Okay. Yeah. So right. So this is the 2 ways of doing it. We prioritize going left at each level, or we prioritize going right at each level. Either way is valid for a level order traversal or breadth first search or breadth first traversal entry. Okay. So let's also talk about in order successors and predecessors. This is something that's kind of important for binary trees, important for graphs. Yeah. So the in order predecessor is a node that lies like right before the given node, and in order successor, or yeah. Okay, in a tree, sorry. In a graph, right, it's just a predecessor. But yeah, in a tree, it's the in-order predecessor is the node that lies right behind the given node. In-order successor is the one that lies right ahead of a given node. So right here, we have a binary search tree, right? And in this binary search tree, the in-order predecessor of 20, or in-order successor of 10. In-order successor of 10, the way we find the in-order successor of 10 is we say, okay, the way we're going to find it is what we're going to do is we're going to go right one time and then left as many times as possible. Because right, like everything that's larger than 10 has to be the right of 10. So we know the in-order successor, because it has to be larger than 10, has to be in the right subtree. We want the smallest thing larger than 10. How do we find the smallest thing in subtree? Well, it's the thing furthest to the left. So we go right one time, get something larger, and then left as many times as possible, get the smallest thing larger. So we go right and then keep going left. That's why 15 is the in-order successor. In-order predecessor is the exact opposite. We want the first thing, we want the largest thing smaller than 10. So how do we do that? Well, it has to be smaller, so we have to go left, has to be in the left subtree. It's the largest thing in that left subtree. So once we're in that left subtree, we have to keep going right. So left, and we go right. So we can't anymore hate the in-order predecessor. So it's 9. So yeah. So okay. So what is a binary search tree? Well, if you remember, a binary search tree is a binary tree in which the left subtree of a node contains only nodes smaller, and the right subtree of a node contains only nodes larger, right? And the left and right subtrees must also be binary search trees. Yeah. And yeah, and it's O log n for if it's balanced for insertion, deletion, and removal. But if it's unbalanced, we have worst case of ON for insert, remove, and find, right? Or yeah, it says, wait, I just realized it says insertion, deletion, and removal. Deletion and removal are the same. It should just say like find and removal. But like, I mean, deletion is also ON because deletion is the same as removal, but okay, that's what they mean. But okay, just for clarification there. But yeah, it's ON if it's unbalanced, of course, because that could be in the worst case, could just be like, what could just be like a linked list, right? In which everything you insert is larger. Oh, it's larger. So if it's not balanced, then you could end up with a linked list. And of course, finding something in a linked list, removing the linked list, or inserting the linked list, it's all ON. Okay. Okay, so proposition number 30. 30, really at 30? No, it should be 24, but okay, whatever. What's the encoding of A? This is a Hoffman tree. So give me a second, try and think about it. Okay. So we talked about this a little bit, I think, last time. So let's discuss. So remember, the Hoffman tree, when you go left, that's a 0. You go right, 1. Go left, get 0. So just read 0, 1, 0. So B. So that's how we would encode it, right? Yeah. So if you go left, it's a 0. If you go right, it's 1. That's how we find the encoding. So what is the letter encoded as 1011? So I'll give you a second to try and figure this one out yourself. You can pause if you want. Now we're going to go over it. So again, right we go 1, or 1 we go right, 0 we go left, 1 we go right. So just 1 and 0 and 1, and our last one is 1. So we're going to go right again. And what do we get? We get S. And that's it. So Hoffman trees, they're full binary trees where all data values for characters are stored in the leaves. We talked about this last time. So the height of the leaves is determined by their frequency in some text. So for example, maybe A here happened 4 times because it's A4. Right. And like then when we actually put together the tree, that's how like we factor in how many times something, how the frequency of something. So the more frequent ones are closer to the top. And directions going down, determine bits. So 0 for left child and 1 for right child. And it's useful for saving bits in storage because it's a greedy approach, which actually is the best way to store this. Like there's no better way. So like you can go back to the greedy discussion if you want to see more details about it. But this is how Hoffman trees work. Okay. So hopefully that covers it anyway. If you have any further questions, of course, message me on Slack or anything. And I hope that covers it. I hope it makes sense. Good luck on your exam. That's about all. Thank you all for watching.